Fine. So welcome back for the session 2 of this FDP on nonlinear problems in mechanical and physical systems. So in this session, we will be discussing about nonlinear dynamics modeling and the methods. So can you see my screen? If anybody, or if somebody can just tell if it is fine.
Yes, sir.
Yeah. Okay. Thank you. So in this particular topic, we will first discuss about under what condition nonlinearity arrives, right? And then we will discuss about the methods which are being used to solve such kind of nonlinear problem. But before introducing those problems, I'll also talk about why really we need to get those solutions, because there are different types of methods available. And if time permits, I will also introduce you some of the numerical methods that can be used for simulating these nonlinear systems. So the first thing that we should always look for a very good reference in nonlinear dynamics, and here I have noted down some of them. So one of the very basic reference is by Thomson, and which is vibration and stability, and this is written in a very nice way, and it also have different methods described in greater detail. So I would prefer that if you are a beginner, you should always try to refer this particular reference. Second is applied nonlinear dynamics by Neffe and Balchandran. He died I think 2 years back, and he was a great researcher and who has developed perturbation methods. In fact, I would say that he popularized perturbation method which is being used to solve nonlinear system, and he was the first editor of Nonlinear Dynamics Journal by Springer. So you will see that he has many students who are faculty in great universities, and they have been continuing research in the interesting field of nonlinear dynamics. So Neffe is the name, and nonlinear dynamics is associated with him forever. And then Balchandran is another professor who is in Maryland, and he worked with him, and he has also written a book in this particular. So this particular reference is another very I would say applied sense. You will find very crucial crucial thing which may not be available in another reference system. It will describe methods. It will also describe uh, non-linear interactions to the greater detail. So if you want to explore more detail about only in the applied sense, then I would refer you this particular book. This book, Neffe and Mook by Nonlinear Dynamics, is a basic book. This one is the basic book which many people refer for understanding nonlinear dynamics. But other than these, there are another nonlinear dynamics book by other authors. So I would not say that those books are not useful. But when we talk about perturbation related methods, so mainly you will see that these books will be of high demand. Okay. Now, if you want to know a little bit more about nonlinear ODE, you can refer this Jordan Smith. And again, if you want to understand the bifurcation, we will be talking something about bifurcation. I'll after some time I'll give you some idea about this particular word in little bit more details. So this book is again little hard, little complex term. They talk in a very mathematical term, but those who are an expert can always try to refer this particular book. Now, what are the nonlinear dynamic problem? You can't really solve it just like that, right? So because linear problem which is doable, that even if you try to see some little complex linear problem, it takes time to solve it. But when there is a non-linearity, of course, it's very hard to get closed form solution, right? So what we try to do is the one way we try to solve such kind of problem is we always look for some numerical solution, but numerical solution cannot give you any kind of physical this or significance in those, like which term is doing what, and then whether it makes sense to vary this term or that term. So those things are very difficult to find out whenever you try to have numerical kind of solution. So people started thinking about why can't we can have, if not complete closed form solution or analytical solution, at least approximate solution, because at least we will understand what is that which is physically influencing the system, and what would be the parameter that need to be controlled for nonlinear dynamics, right? So uh, so there are many softwares that, and you will see that nowadays there are many upcoming softwares which are coming, and still there are a lot of work need to be done. So the first attempt to bifurcation that I will talk about. So let me just first explain to you what is bifurcation. So let us say a system is moving like this, okay, and it is a stable system, right? Now, suddenly, after some parameter change, let's say this system is dependent on some damping factor mu, right? And when the damping varies, it is stable over here, and suddenly it sees that the system is divided into two parts. Okay, so let us say this is again a stable solution, all right, and this is unstable solution. Okay, this is one example where you see that suddenly for a given mu is equal to mu star, what is happening? The system started from stable solution and then it bifurcated into two solution. In one of the solution becomes remain stable and another solution become unstable. It means that after mu is equal to mu star, the stability of the system changes, right? So there are two things that you will see: the nature of stability, right? And second, the quantity of stability. So when we have these two changes, either one of them or both. So either one of them, example will be, let us say you have a stable system and suddenly it becomes unstable. So the solution remains one only even after this, right? But here it was stable and here it is unstable. So nature of the solution is changing. So these points where such changes are happening are called bifurcation points. Okay, and they are function of some parameters that vary. It can be a force, it can be damping, it can be any parameter that is governing a system. So by varying that, you will find that the system changes its nature of the stability or the quantity of the equilibrium solution. So such kind of points are called bifurcation points. Okay, and that is very important in terms of nonlinear system, because after some time you will see that the solutions are always dependent on some factor. So that's what is called bifurcation. Another example you will see, many of you who are mechanical engineer, you will know that, or even from other field, there is a harmonic oscillator, right? The harmonic oscillator is something like this. This is how basically we describe it, or Lorentzian oscillator, right? So here you will see that the system is having a very symmetric curve, right? And it has a peak corresponding to a given omega. So that omega, which this can be your forced frequency, and this can be near to your resonance frequency. So let us say this is resonance frequency. So when your forced frequency varies from low to near to the resonance frequency of your system. So you will see that the response reaches its peak, and we call such kind of frequency as resonance frequency. But this happens only when you try to describe for that we can also think about what kind of system is it. So let us say you are having a spring, you are having a damper and connecting it with mass m, right, and you are just fixing it over here, right? So in that case, we are assuming that this k is linear. Okay, when we say that what is called linear, so if this is x is your deflection, so the spring force we say that is a linear force. In this particular case, this force will be minus k times x, right? So it is directly proportional to your displacement. Similarly, we call this damping as viscous damper, right? Viscous damper. So in this particular case, it is also proportional to velocity of this particular mass. So if you write it in equality, it will become minus cx dash. Okay, so until now, whenever we talk about a linear system, okay, so this is your linear system. So in this case, we are saying that the spring is a linear spring and the damper is viscous damper, in which it is directly proportional to velocity. And if we look for its resonance frequency or natural frequency, first of all, under free vibration, so you will see that it is written by k by m, right? So this is how basically it varies. Now when you apply some load F, forcing, harmonic forcing, and vary it by let us say F naught cos omega t. So this omega which you will vary. So if you vary this particular omega from here to here, you will see that when omega reaches near this natural frequency, the peak is found. It means that your system will reach highest response corresponding to its resonance frequency or natural frequency of the system. Okay, so that way we try to pinpoint this response. But these kind of response is valid only when the oscillation of this mass is small. Now, what is the under what condition this is small? This oscillation will be small. This oscillation will be small if the magnitude of the forcing F is kept small for a small forcing F naught, right? So now what will happen if I start increasing it? So when we start increasing it, it may happen that the spring which was behaving linearly, right, it may become non-linear. So it will have one component which is linear, another component which will become non-linear, right? It may happen this C may also be, one is your viscous damper, another one is your non-linear spring component will come up. So, and it may depends on, there can be different types of non-linearity. For example, here the force under this condition is directly proportional to your velocity, right? Similarly, here it can be directly proportional to minus x time x dot or x dot square. So these are all non-linear kind of damping that may introduce. So the question is, will the response remain same, right? So the solution is, the response is no, it will not remain same. So as you increase your forcing amplitude F naught, right? So what will happen? It will keep on going like this. So initially it will go this way, right? But there will be a point you will see that symmetry is breaking, right? Symmetry is breaking. It means that beyond this point, if you try to increase, what will happen? The response will be something like this. Okay, but so we will discuss more about these kind of response in the following slides. Okay, so getting solution of linear range, we don't need any special kind of solver. But when you deal with a non-linear response like this, okay, response like this. Now the question is, when you try to find out the solution of such kind of response, correspond. So this is your amplitude, right? And this is your frequency. So here you see that corresponding to this frequency omega 1, you have a unique solution, right? But at the same time, the same solution repeats corresponding to this. So if you just keep on going here, corresponding to each, here you are getting unique solution. But the moment you cross this region, right, here, let us say. So what you see here is you are having solution 1, 2, and 3. And such kind of solution is multi-variable solution. So it means that response amplitude is having 1, 2, 3 solution. But the question is, how to find out numerically this solution? Will you be able to apply? Will you be able to get this solution numerically? This is the biggest question. So the answer is you can't. You can get things individually. If you try to get a numerical solution using let us say Rangagutta method, you are going to have something like this. From here it will jump and then you will get this. So this is like a forward sweep. When you sweep your frequency like this, but what will happen when you sweep the frequency in the backward direction? So it will come here and then it will go this way, and here you will see again it will jump here and then go like this along the same path like this. Okay, but you are not going to get this reason. Okay, because it is an unstable reason. Okay, so how do you get those kind of curves? So you get those kind of curves, either you try to get some approximate analytical solution or you use bifurcation tools and wherever. So here, as I said, I explained you the concept of bifurcation, and here also the same thing is happening. If you reach here, there are two solution, no solution, and one solution which is jumping to some other state, right? This is also a bifurcation. So the two points are there. One point is this, another point is this, and they are called saddle node kind of bifurcation. Okay, but in simple term, you will see that the solution is splitting from here or jumping to some other state, right? So it is called bifurcation point. This is also a bifurcation point. So all these bifurcation diagrams can be obtained using different types of software. So the first software that came into existence was Auto. Okay, Auto has been used by many people and still many people use it. It has lots of features. The only shortcoming is that this one is written in Fortran. Okay, this is in Fortran. In MATLAB, when you write the same code which is written in MATLAB, of course it takes a lot of time, lot of space based on how this curve is trying to move. I will talk about different intricacies related with the solution of numerical simulation of these curves later. But for the time being, the thing is whatever is written in Fortran, and it was written in Fortran because to speed up the process. The same thing if you try to write in MATLAB, it will not be that fast. Okay. So after MATLAB became popular, some people got together and they developed one library, okay, which is called MATCONT. So it is a continuation tool, or I would say that continuous library that is available freely. And after you install MATLAB, you can always install MATCONT and then work. In the next session, Prashant will be teaching you how to use MATCONT and here I'm just like mentioning it for your information. Now, another software which is required, I would say. So one is Maple or Mathematica. Either one of them you should be using it. I will just make my uh, space little clear. Okay. So here you see that so up to this it's all MATLAB, and here you do play with the data and try to get the solution. Now, if you don't want to play with the data, you want to get the solution use in terms of some expression. So this is where like these softwares, which is Maple or Mathematica, with whatever you are comfortable, you can use it, and using these tools, you can get a solution in terms of parameters, or we call it as a symbolic calculation can be performed in these two softwares quite easily. To a greater detail, because it has a lot of libraries, lot of solvers which are quite optimal. Now, very recently, so there is, I would also mention, uh, like MatCont, Offlet, there is another tool which is called Coco. Okay, so Coco is again a continuation tool, but a tool which is developed by another researcher. Okay, so people, however, we see that this is quite popular, and this has also been used by many, but you need to find the difference and limitations of each one of them. Okay, so the third generation, development that is happening in nonlinear dynamics tools is called SM tool, which is smooth manifold method. So here, this is everybody is having a closer look at this tool which is coming up, because it not just help us to simulate data in terms of lumped system, but I think this also helps us to not just reduce the time, but because sometimes when you deal with nonlinear system, there are a lot of solutions. Now the question is, which solution is important and which one you are going to take. Okay, so the solution which is important near to a given frequency, you try to take that particular uh, uh, particular vector, and based on that you try to do simulation. Okay, so there are very detailed theory that have been developed by a professor in ETH Zurich, and they have developed some library also. So I would recommend that you should, those who are very seriously looking into nonlinear dynamics and want to really explore further development, try to learn this. This is a very interesting tool which is coming up. Okay, so these are the things which are, so I would say that try to have, either if you are comfortable working with auto, you can do many things. If you want to work in MATLAB, you can use this, and library is this. This is also written in the MATLAB Coco. Okay, and then Maple and Mathematica are used for like this symbolic kind of calculations, that Prashant will also give you some example of the uses of Maple. Okay, and SM tool example will be given by the last speaker. Okay, he will talk about this particular tool, and Prashant will be talking about MatCont and Maple and their application in solving nonlinear problem. Okay, so let us start a little bit more fundamental. Now, why we need to really look at the dynamical system? So, of course, we define a dynamical system as the one whose state changes or evolve with time. So there is a term you will see, that evolution. Okay, evolution means as the time progress, how the solution is changing. First, you will see that if I take a linear system, okay, so based on if it is a free vibration and I give you this initial condition, right? If this is like initial condition, so it will keep on vibrating. right? Keep on vibrating if it is undamped, right? Undamped free vibration problem. Now, if I make it a damped one, damped, of course, free vibration, then what will happen? It will start. Maybe I'll just change my screen. 1 minute. Okay. All right. So, I'm sorry. So when I start, when I assume damped vibration, so here you will see that it will start from here and start, decreasing. The amplitude will start decreasing, and there may be a little bit of change in the frequency, which we call as a damped frequency, right? If you remember, so little bit of change will be there. Otherwise, you will see that the amplitude will keep on dying exponentially under the damped condition. So, and I'm not going into when I say damped condition, I'm basically referring to some undamped, underdamped kind of condition. I don't want to go into the overdamped or critically damped system right now. Okay, so this is your under damped state. So if you don't apply any force and just give initial condition, for example, over here. So here is your mass, sorry, spring, damper, and then mass. This is one state that we started. Now what I am talking about, and before that, if you don't have any damping, only spring is there and your mass is there, right? Mass, K, K, and C. So in this particular case, the first one that was there where we didn't have any damping, right? So it will keep on oscillating with the same amplitude and with its natural frequency. Now, when there is a damping, the frequency changes to damped natural frequency, and the amplitude also changes exponentially. It dies down basically, right? But now, if there is a case when you are putting forcing, right? So in that particular case, what will happen? These were your free vibration problem. And let us say the solution corresponding to that is, which we also called complementary solution or transient solution. Okay, so we call it, the solution under free vibration will be called transient solution or complementary solution. But when you try to look for some forcing, let us say f naught cos omega t. So what will happen in this case? The system will vary something like this. So you started with the initial condition, right? It will go, if you are also giving some velocity, so it will have some upward trend. It will go, sorry, I think it should be having same frequency. Okay, so let us say it is going like this. And then it will keep on oscillating. This will remain constant. Okay. So what is happening? You are having some reduction, and then the solution becomes steady, right? So it means that when you do this forced kind of excitation, the solution consists of transient, where it dies down based on what is the damping level, and then it becomes steady state. It means that after some time only your system will be steady state, in the steady state. Okay, So whenever we try to deal with the forced vibration, we always look for the steady state response. Okay, steady state response. So it means that numerically we have to see solution after some time, not immediately, because in the beginning you will have a transient solution even for the forced vibration system. So when it dies down, then it becomes a steady state solution. So that is, so here you see that amplitude is also changing. It may also come down. There is a possibility that it can also go up, okay, and then become steady. So it means it is changing like this, right, and become constant. So these possibilities are also there. But what we need to understand, what we need to understand that we are looking for only steady state solution numerically when we get. But your system may give both the solution, transient as well as steady state. So what is the frequency content in the transient region and what is the steady frequency content in steady state? So in transient state, you are having combination of your natural frequency and forced frequency. So here, this is your forced frequency, and here your natural frequency is under root k by m, which will come out from here. Okay, in case of damping, this will be under root omega n 1 minus this square, which is called damped natural frequency, right? So in this particular case, you will see that in the transient region, you have a frequency which will be consisting of your natural frequency and forced frequency. But when you go to your steady state, okay, this will die down. Vibration having natural frequency will die down if there is a damping, okay, and the steady state will have frequency only the forced component. So whenever we try to see response, steady state response of nonlinear system, we always look for the amplitude in the steady state. So it means whenever we try to plot, let us say corresponding to omega 1, so I will look at this amplitude, okay, and you will see that I'll cross it here. Now at different omega 2, it may happen that this will increase, right? Steady state response will increase. So it will come, amplitude will be this. So A1, here it is A2. So what is A1? A1 is corresponding to this A1. And similarly, when I change omega, this A2, this amplitude of steady state response will again change. Okay, so this way we keep on plotting the curve and it will just go something like this. Okay, so you'll see that there is a jump and then it will come this way. So whenever we try to plot, nonlinear response, we always focus on the steady state and its amplitude and try to see this. So here you see that as this forcing amplitude is changing, if the system goes transit from linear to nonlinear regime, so you can change the solution also changes accordingly. And this change we call it as the evolution with time, right? So here the solution is changing, evolving with time. So these are all dynamical system. It is not a steady state system. But if the system is such that you are putting something and it is not changing with time, okay, so this is called static system, right? So but there is something called quasi-static. So initially it will go and then it will become constant. So we just neglect those effects. But at a longer state, you will see that it is invariable with time. Okay. So these are the terms which are associated with nonlinear dynamical systems. Now, so when we understand we are dealing with dynamical system and solution or states evolve with time. Now the question is, what is the state of a system? Okay, so when I deal with a equation, let us say x dot is equals to f of xt. Okay, so here whatever number of x appears in this state space form, they will form the states of the system. So when you reduce your equation into this form, okay, so they are called the states of the system. All right. But physically, what are the states? Physically, we define states as the minimum number of variables which will be sufficient to describe the motion of your system itself. Okay, so the minimum number of variables which are required to describe the state of the system at any given time is called the these are called the state of the system, or we'll also call it the degree of freedom of the system. Okay, so any items will vary with time. Any degree of freedom, if a system is having 2 degrees of freedom, so each component will vary with time, right? So these are some of the things that we have to keep it in mind. Now, these systems can be two types. One is discrete or continuous. Now, what is discrete? Whenever we try to deal with, so here you see that this is a very it's a continuous kind of equation, right? Because differential equation exists over here. But for sometimes, so in this case, your curves will be quite smooth. It will vary nicely like this. There will not be any ambiguity. But let us assume that this particular system is having 10 to 20 frequency component. Now, how the response will look like? The response may look like something like this. Right? So you see that there is a pattern, but that is a different level. It means that this signal contains more than one frequency component. It means more than one time period of repetition of the patterns, right? So here you are having multi-frequency component. So it is quite natural over here that describing this system is very easy, but describing this system using the transient response, when I say here x versus time, here x versus time, so here it is easy, right? But here it is not easy. Because we don't really know how the amplitude corresponding to that frequency your system is having. There are n number of frequency component in it. So we try to look for some alternate techniques to describe the system, and there are different ways. One is called your phase space, right? Phase plot that we plot versus x dot versus x. Second one is Poincaré map. Request you to, if you have question, please ask. Otherwise, please mute yourself.
Sir.
Yeah.
Sir, in multi-frequency system, how to find the steady state and transient state?
Yeah. So even in the multi-frequency state, you will see that there will be a pattern that will be formed. So what we do is after you see that for a long time, if the variation is going in the same way, so we take, for example, let us say we assume that up to t naught time, right? We have some transient which has died down, but after that things have become steady. So you take from the last, let's say 1000 cycles you have taken, and out of this 1000 cycles you want to take up to 500 cycles, right? And then you try to find out the FFT of this signal. So when you try to find the FFT of this signal, you will see the frequency component, how many frequency components are there in that particular signal. Okay, so that way we try to catch up those things. And again, as I said, in that case, the concept of transient basically becomes very weak, right?
Yes.
So in that case, we just what we do, by first we plot the transient response for a longer duration and then see if we are getting the proper steady state. So those transient proper steady state will also we have some kind of pattern which will repeat. It may happen that after 3-4 cycle it will. So here you can see this and this is repeating, right? So one time period is this and this is repeating. This is another time period. But initially, if you see, there may be even more. Okay, so those will filter out. By looking at the graph itself, you will figure out that there is a little bit of transient in the beginning, and from the end you can take as many cycle as possible to include all this frequency component, which would be more or less clear, and then you can plot it. Second way is you take a whole signal, whole time signal, okay, and then you take FFT. When you take FFT, you will come to know that okay, there is a frequency of your natural frequency also, which is
Okay.
associated with the transient, that will
Oh,
die down. So so that way also you can try to know that what are the frequency component which is there. So in other word, telling that it is really very difficult to treat with a signal which is having so many frequencies component, and also its amplitude is
okay.
not. So these are the techniques that we have to deal with, and to understand it better, there are different techniques that we follow. One is your phase plot and then Poincaré map. In the Poincaré map, because it is very messy, right? This signal is very messy. So what we do, we find out the time period of all this frequency component and select the minima of the whole time period. Let us say time t1, t2 dash 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 tn. Then you collect the amplitude. So as I said, so let us say here is your graph. So initially there is a transient, and then suddenly you see that there is a some 2-3 components are there, let us say. Okay, so the time period corresponding to that, I see that. So what I will do, I will select this as, let us assume this t minima, okay, of all the signal of the frequency component. So for every time t, I will take the snapshot of this signal. So here you see, if I take a snapshot, I put my camera on here and then I'll again select over here, then select here. So you see that if it is a periodic signal, then every time I'm getting only one curve. Okay, in the
Okay.
Poincaré map, you will have only dot, one point,
Yes, sir.
if it is periodic signal. Now if it is having two signal, you will have 2 points, right?
Okay. Okay.
If you are having three frequencies, you will have 3 points. If you are having, let us say, 5 frequency, you have 5 point. But there will be a point when such kind of frequency component rises, okay, and the ratio of those frequency components are irrational, then we talk about quasi
Periodic.
periodic system. Okay, so what is happening? We started with periodic system, right?
Mm.
This is at low f naught, which is your f naught means loading. Now when you increase this loading, it may happen that the system will start showing up more than one frequency component. Okay,
Okay.
so that is the beginning, that condition is called quasi periodic. But if you keep on increasing this f naught, then what will happen? You will have multi frequency component, and those frequency components ratios, if they turn out to be irrational, you will see that there may be chaos. Okay,
Yes.
chaos will be formed. So before chaos, system always give you this indication, quasi periodic condition. So if you are able to control your system at this level, this catastrophic effect will not be able to come. But people are trying to understand this also. But how to really see this when you have so many component in chaos. So it means you will have so many points, right? It will have so many points, and in many cases you will see they are having some kind of patterns. Okay, they are having some kind of patterns. So so this is how things happens. This is very important whenever you deal with the numerical solution of this system. Is very important. So here in this graph Poincaré map, you see that whatever was very smooth continuous curve, here it is just like a point. Okay, so this type of system is called discrete system. Discrete system, this kind of system is called continuous system. Even another example of continuous system is phase plot. If you try to do phase plot x dot versus x, so if it is a periodic solution, you will see a closed curve. If it is quasi periodic, then you will see a curve which is something like this. Okay, so like two closed curve. So the number of closed loop that you get in phase plot, that will also indicate how many frequency components are there or periodic solutions are there. So but here you see that still it is a smooth curve. Okay, so this is another example of your continuous system. This is continuous system, this is continuous system, but this is discrete system where we are having only points. So it means that the equations for these two kinds of systems would be different, right? Example of continuous system. Continuous system is this that I gave you. An example of discrete system is like a map. N plus 1 is equal to fxn. So it is this, the evolution of this point depends on the initial point xn, right? So this is called map, and this is called flow. Okay, so in nonlinear dynamics, whenever we deal with the continuous system, we talk about the flow equation. Whenever we deal with a discrete system, we call about the map equation. Okay, so this is the difference. So when you talk about discrete system, we discuss about a system of algebraic equations, which is these. Here no evolution time, no evolution of the time is there, right? In continuous system, it is the evolution of time, the function of time that you get, smooth solution that you get, and that will be described by a system of differential equations. Okay, so these are the two main systems that we discuss. Now coming to the type of solution that we get in the dynamical system, it can be a fixed point, right? It can be an equilibrium periodic solution. It can be, this is also called a stationary solution. I'm sorry, this is not periodic. These are all the different names which we describe for a constant solution. So that can be called fixed point, equilibrium point, or stationary solution. Now there the solution can be time vary. So here it is called dynamic solution, but it is also called either periodic solution, right? Aperiodic solution. There may be different types of solution that may exist. Okay, with the time varying that we get it. So these things we need to keep it in mind. Now, what are the?
Hello, sir.
Yes.
Sir, when we are going for this mapping with the Poincaré method, so it's told if number of frequencies are there, we will get that much number of points, right?
Yeah. Yes.
So and the plot is drawn between some snap points, like some
Yes.
time interval.
Yes.
So how do we select that time interval? Because
So
if
yeah.
that
So
time
yes. So that's what I told you, that this is very important thing. So let us say you are having frequency components f1, f2, f3, and dash, right? Now, same way you can find out the time period, right? So the corresponding time periods, let's say T1, T2, T3, and Tn. So let us say these many components are there in your solution, and the corresponding time periods are given by this. So you have to select this time of short is the T minima. Okay, T minima is the minimum of all this T1, T2, dot 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 Tn that is existing. So if you take a shot every this time, then you will be able to capture all the component of these frequencies. Okay, if you take a shot more than this time, you will miss out some of the frequency components. So this is what you need to do it. Okay. Is it okay? I hope it is fine.
Okay, sir. Okay, sir. Okay, sir.
Yeah. Now, under what condition you can have nonlinearity? So it may happen that your material behaves nonlinearly. For example, if you remember your elastic material, so you'll say that stress versus strain, it varies linearly like this, right? So that is one. So this is called linearly varying or the linear elastic material that we talk about. So because when we write the governing equation for the deformation of any flexible body, right? So in that case, these stresses, how they are varying, it is also important. So and in nonlinear case, what will happen? It will vary like this. I'm not going into the ultimate limit and beyond that, because we want to just consider the basic concept of how things may vary. So if you get this kind of relationship where stress strain relationship gives you nonlinear response like this, so the associated nonlinearity is called your material nonlinearity. It means that at the material level the characteristic is nonlinear. It's a nonlinear material kind of. Now there may be another kind of nonlinearity. Another kind of nonlinearity in a sense. Let us say you take one rubber. Okay. So if you stretch a little bit, then what will happen? Uh, it will it will just get stretched, but you will not see much of the deformation coming up. But when you stretch is longer, you will see that it will develop a very strong tensile force and it or restoring force towards inside, and that will become non-linearly. So it means that those forces will become dependent on the displacement as well. Okay, so under that condition, we get some kind of geometric nonlinearity where your deformation become or the characteristic become the function of the deformation also. Okay, so this is mainly related with the large deformation case, which is called your geometric nonlinearity. Now there may be another kind of problem where nonlinearity may come up, so which is your contact problems, right? And in another case where the loads may vary faster as compared to your frequency of your structure, so those are also somewhat non-steady kind of case, and it may happen that things may go down to your nonlinear. And then there are different cases where boundary condition may vary fast. So your for example, freezing of water or welding, so there the change in temperature happens quite fast, right? So how to model that? So ultimately the system that you get, you may end up having a non-linear kind of system. So many things matter. We can't just say that non-linearity is simply because of geometric means because of large deformation. It can be material non-linearity. There can be like boundary condition which is non-linear. There may be like the contact problem, large deformation, large contact problem that is happening, where additional stresses are being developed. So non-linearity can arise from different factors. So we should be very uh, careful when we try to find out the solution of a system. So the first thing we need to figure out, what kind of nonlinearity is existing in the system that you are trying to model. Okay, that is the key, and that is very important. Okay, so uh, so these are the general type. Now let me just explain it to you, geometric kind of nonlinearity, and for this I'll take a pendulum, simple pendulum. So here it is hinged, right, and you have a mass here. So if you just deflect it from its equilibrium position, this is your equilibrium position, and if you just pull it and leave it from here, what will happen? You will have forces, restoring force because of the gravity, and this will try to pull over here, right? So when you try to write down this equilibrium equation, so motion is happening in theta direction, and the forces which is acting in that direction is your mg sine theta, which is in the reverse direction, right? So when you write the equation of motion, so basically you will see that it is having sine theta component, right? So ultimately you will get something like this: m theta double dot is equals to double dot and L, and here it will be your mg, sorry, plus mg sine theta is equal to 0. If you take that into other side, this is what ultimately you are going to get. So this is your acceleration related term, right, dynamic term, and this is your external force which is acting on your body, which is giving this motion. So ultimately the equation that you are going to get is g by L sine theta equals to 0. Now what is this? This is your actual equation of pendulum, which is this. Okay, this is your actual equation of pendulum. Now when we assume that this theta is small, okay, when theta or displacement is small, in that case what is happening? I can write, if you just expand theta, how it is: theta minus theta cube by 3 factorial plus dot dot dot, right? So if my theta is small, for example, let us say theta is 0.01, right? Now what would be theta cube? It can also be 1 into 10 to the power minus 2, I can write. So what would be theta cube? Next term, theta cube will become 10 to the power minus 6. You can see this first term itself is so much large as compared to the theta cube term, right? So if I assume that my vibration theta is small, of the order of 10 to the power minus 2, or even if I take 10 to the power minus 1, right? If let us say if I take it is of the order of 10 to the power 1, which is 1 into 10 to the power minus 1, then what is happening? Your theta cube will become 1 into 10 to the power minus 3. It has reduced by second order, right? So it means if this is 0.1, this is 0.001. So you can see this term is so small as compared to first. So if theta is small, I can very easily approximate sine theta as theta without putting any error, and the second, like the error which will be of the order of theta cube, okay, which is, let's say, these values that you see, and that's why one can neglect this higher order term. We call it as higher order term. So when you just replace this sine theta with theta, you get to know this particular equation, and this is your linear equation of pendulum. And when we compare this with harmonic oscillator, which is omega n square theta is equal to 0, we get the natural frequency, which is your omega n is equal to under root g by L, right? This is what you get it. So now the question is, what if the deformation is large? If theta is not 0.1, but if theta is, let us say, near to 0.9, right? So what would be theta cube? Theta cube will be your 27, right? So that way 1, 2, 3. This is what you will be getting, right? So 0.9, then you will have this value. But you'll see that they are quite near, right? It's not that the second order of change is not there. It's just one order difference is there, because here it is 9 e to the power minus 1 and here 2.7 e to the power minus 2. So the change is just one order. Here the change was two order, right? Minus 1 to 1, 3. It means that if theta is of the order of 0.1, so the second term may also become important. So when second term become important, what you get? Your equation, this equation that you are having, this will become g by L theta, right? And minus g by L theta cube by 3 factorial plus of the order of theta to the power 5. Of course, when you substitute this one in 5, it will be much lesser as compared to this. But at least this one is little bit one order less than theta. Now to represent its magnitude, which is less as compared to theta, what do? We write such kind of equation as, let us say omega 1. For the time being, I'll just consider it as 1. Okay, so this will be theta, and this I will write it as epsilon times theta cube. Okay, so what is this epsilon? So epsilon says that if the order of this term is 1, right? The order of this term is 1, order of this term is 1, but the order of this term is a small quantity epsilon as compared to these two terms. Okay, so it means that there is a term which is little weak as compared to other two terms, which may be significant immediately if we go from 0.1 to 0.9. Okay, so this equation, in that case, the weak nonlinear equation we call it, is can be approximated as theta double dot theta. Let us just take, so as I said, let us assume this as 1 theta plus epsilon times theta cube. Okay, so the first approximation is this theta cube, and the form of this equation we call it as a Duffing. Basically, the initially found by this gentleman, so it's called Duffing oscillator. Okay, or Duffing equation. This is your harmonic oscillator or Lorentz oscillator, right? And this one is your Duffing oscillator, where we are having this cubic nonlinear terms coming into picture. Okay, so this is, and you'll see that when this when this epsilon is the one which helps us, to get some approximate solution of the nonlinear equation. So this approximation that we are having, it may happen that when you are having even more large deformation, it may be near to 1. So when it is near to 1, it means this term is of the same order as this, and we call such kind of equation as a strong nonlinear equation. Okay, is a strong nonlinear equation. Now when this epsilon is very less than 1 and it is written like this, we call such kind of equation as weak nonlinear equation. And this is a strong nonlinear equation. So not all strong nonlinear equations can be solved in the closed form. Okay, so what we do, we always try to get, because most of the linear equations you can solve, even little complex linear equation have some very different form, right? So when you talk about nonlinear, it is difficult. Okay, so we to solve such kind of equation, we deal with a method which we call as the perturbation method. So this is what we need to understand, how this perturbation method work, right? So let us first let me clear this. Yeah. So we discussed about all this under large deformation. This is your equation, and then so we define this equation as this. And if you try to get the analytical solution of this equation, so it is very simple because it's a harmonic oscillator. It would be a function of sine or cos. So either you can write like this, right? And using two initial conditions, you can always get these constants. Alternatively, you can also write this solution as C, right? C cos omega t minus phi. So here C is unknown and phi is unknown. So again, these two can be found from these two initial conditions. Okay. Now after you substitute this, so this is how basically it will look like, and you see that these are the initial conditions which are there, right? And alternatively, again you can write it in this particular form. So finding out solution of linear equation is easy, and just to get a solution of nonlinear equation, okay, nonlinear equation which is of let us say epsilon some gamma times theta cube, or some, yeah, something of this kind, let us say. So this represent a smaller number, and gamma represent, it's not exactly same as this because it will get divided with cube, right? So that will be you will have omega squared divided by 3 factorial, right? Which is coming from here. So that we will have to write it as a separate factor, which is your gamma. Okay, so that way you can, or alpha, whatever term that. So this is what is your next immediate weak nonlinear equation that we need to deal with. And it is always simple or convenience to do certain kind of non-dimensionalization. Okay, right now whenever, so that is another very important procedure that we need to adopt when we deal with the nonlinear equation. So here you are having a time scale which is associated with omega. Here theta may also be having some time scale, right? It is in radians that you are putting in. So for nonlinear equations, there is one step that we need to do is from original equation, okay, we need to convert it into non-dimensional equation through different definition of the terms. For example, you can have let us say omega is one term, right? So whenever so omega is your 2 pi f, right? And f is your 2 pi by t. So it means that there is a time period t which is associated with omega. So if I define new time that varies as let us say a small time t by divided by, either you take it as this omega as the time, or this time. So either you can do it like this, okay, or you can do it many times people do in this way. So this is also another type of scaling that we do. So the time, because omega is of the same, it is directly proportional to your f. The only difference is 2 pi comes up. So that way things become a little complicated. Otherwise, you can just take this form as the non-dimensionalized form and do scaling of this time series, right? Here you are having theta double dot d2 theta by dt square. So here time appears. So here you will have to substitute t star divided by omega. Okay, so because it is 2 times, so you will see that omega square will come up. So what will happen in this case? It will become omega square d2 theta by dt star square, right? So this square and this square will get cancelled, and you will be having simply theta double dot with theta, but here the time is now t star. Okay, So these kind of non-dimensionalization also we do, so that when we try to develop the solution, it becomes in terms of those non-dimensional form. Okay, and we are able to capture something a little bit in a better way, or we can visualize things in a better way. So we will talk about this time scale and their effects also as we go along. Now coming to your non-dimensionalization, and after non-dimensionalization we discuss about the solution method. Okay, solution methods. So these are the things which are there, and so here for nonlinear we always look for approximate analytical solution. Of course, you can go for nonlinear solution, but numerical solution, but right now we are not looking at. Yeah. So now the question is, this is just for scribbling, which I have been doing it for in other slides as well. So right now we don't require. So now there is another kind of classification which is very important. So your system, continuous system, which can be, because whenever we try to get the final form, we also need to understand whether your solution is autonomous or non-autonomous kind. Okay, so when the time appears in the equation explicitly, we call it as the non-autonomous system. Here, if you see, if you look at this particular example, here what is happening? The time is appearing explicitly into the equation, right? So we call it as non-autonomous system. But when you convert it, when you take time also as one of the state, right? And when you see that it doesn't appear into the system explicitly, except that the solution is varying with time. Here it will be like dx1 by dt, dx2 by dt, right? So here time is appearing, but here it's not appearing. So such kind of system where the time doesn't appear explicitly is called autonomous system. Okay. So what we do basically when we have nonlinear equation, like here you are having omega square x, and you can have some term nonlinear x cube term also coming over here. So we need to first convert into a form which is non-autonomous, and from there we try to get the solution of some envelope equation. That is the form that we try to get using perturbation method. Okay, so what are the methods which are available? Do you want some break of 2 minutes, 3 minutes, or shall we continue?
Continue, sir.
Sir, continue.
Okay, thank you. Yeah, thanks a lot. So coming to the solution method, there are many methods, but so these are all called perturbation methods. Okay, so one is your straightforward expansion method that I will be describing. Second one is methods of multiple scales. Then method of averaging. Prashant will be describing in more detail about methods of multiple scales. Then harmonic balance method, and there is another method which is called normal form method. So here these methods are good for weakly nonlinear system. Okay, but if the nonlinearity increases, for example, as I said, when you have your equation which is written like this, x cube, right? So here epsilon becomes 1, right? So this is, it means it is a strong nonlinear system. For these kind of system, you can't apply these methods. Okay, for strong nonlinear system, normal form method works well. So this can be used for any normal form method. However, these methods are used for only weakly nonlinear system, and we always try to first explore the weakly. For example, if my system just crosses the linearity, then what happens? This is what most of the time we try to get it right. So under that condition, we call it as weakly nonlinear system. So we were discussing about these methods. It's also called perturbation methods, right? This is what is being written here. So let us discuss about this straightforward expansion method. Okay. So as I said, this is a small quantity, which is your epsilon, and it represents the weak non-linear term. Okay. So let us consider equation, general equation. So here it is x double dot x. So these terms are of the same order. Here you can see it is of the order 1. This is of the order 1. But this term is of the order epsilon. But what is epsilon? Epsilon is a small quantity or a small number which varies from 0 to 1. Okay, so it means that this term, just to represent that this term is smaller than these two main terms, which are form of linear term. If you in other way, if you try to see that epsilon to the power 0 term, you will get only x double dot plus x, and this is also a linear equation, right? It's a linear equation. But when you deal with epsilon to the power 1 term, then you will get this particular term getting activated or becoming significant, right? So how do we solve it? So to solve it, generally we can express our solution as a power series of this epsilon. Okay, so what is this power series solution? The power series solution is written something like this, that you write it as epsilon to the power I xi, okay, and I varying from 1 to n. This is your power series solution of this x. Okay, this is a straightforward expansion method, we call it as. So it means that I want to have a solution uh, which is also of the order of different order of this small number epsilon. So it means I am dividing my whole solution as x naught. So x naught will be of the order of epsilon to the power 0, which is nothing but 1, right? So it means that this solution basically is related with only these two terms. Now there is another solution x1 which will be of the order of epsilon. Okay, epsilon to the power 1 means epsilon. It means that this solution will be affected by this term. Okay, so ultimately when this nonlinearity becomes even more stronger, we keep on going to the higher order term to capture uh, accuracy of the more accuracy of the solution. Okay, but when we just deal with very weak solution, we just try to have first two term. So this is your linear solution, and this is your first order approximate solution. And if you want to increase the accuracy, you can just keep on going like this. So this is called your straightforward expansion method. So in that particular case, a straightforward expansion method, this is how basically we did it. So let us try to apply this and try to see what is the problem when we try to apply it. So it can work for many problems, but it will have uh, it will as and it is also valid for very small time. Okay, this solution, this straightforward method can work only for a small time interval, but as the time increases, you will see that for some of the system the solution will start diverging, and this is where it fails. Okay, so and remember that here we are not changing anything related with this time. We are keeping the same time as the original time of the system which is appearing over here. Okay, there is no change in the time. So let us take this simple equation, which is x double dot plus x is equal to 2 epsilon damping. So it's a damping problem, and we are assuming that this damping is little small. Okay, and these are initial conditions. So starting with this approximation, which is your x, and it goes at epsilon naught x1, epsilon to the power x2. Now if you substitute this solution over here, okay, x double dot plus x is equals to 2 epsilon x dot. You simply have to substitute it. So if you substitute it, what you get is here for each you are having one differential equation, right? So here you are getting, so we call it as, this is how it will be called. So in place of your x, you are doing it, and this time basically we are denoting it by d2. Okay, so this d2 is nothing but, sorry, not this, this one. Okay, this is your d2, and this first order that will appear over here, right? So that first order is your this dy dt2. So representing d as dy d2 and d2 as d2 by dt square, we can write this component as this, and in place of x we can simply substitute these values, right? Here you can see. Similarly here only simple substitution of this term will be there, and here again now the question is, this term, this damping term is one order weaker than these two terms, means your spring term, stiffness term, and inertial term. This is called inertial term, this is called stiffness term, right? So these two terms are little one order higher than this as compared to a factor called epsilon. So when you substitute x dot from here, so what will happen? That term will get multiplied with this epsilon. So whatever was epsilon naught, it will become epsilon 1. This will be epsilon square and all that, right? Now, after substituting, you have to compare the coefficients of all this epsilon. Okay, starting with I is equal to 0 to 1, 2, dot, dot, dot. As many solutions. So whatever number of approximation you want, that many epsilon you will have to use. Okay, so if let's say I'm just keeping two terms, in that case I will just go ahead with epsilon to the power 0 and epsilon to the power 1. I'll not go for higher one. If I am taking approximation up to this, I will be comparing coefficients from epsilon to the power 0, 1, 2, and 3. So that way you will have to decide till what value you are going to do it. So when you do, the coefficient of epsilon to the power 0 gives you the very first equation, and this is nothing but your linear equation, right? Epsilon to the power 0 term gives you just the linear equation, which is this, and we know the solution of this equation, right? If you remember, initially we found the solution of this equation is same as your linear equation or harmonic solution, which is written as a sine t, b cos t, omega here is 1, so that's why omega is not over there, or you can write it as c times cos t minus phi. Okay, so that way also you can take this solution. And third way you can take the solution is the real component of a e to the power I omega t. So omega here is missing, plus conjugate term that you get here is e to the power minus I omega t. So this is your basically the alternate solution when you try to express solution in terms of exponential. So you can make use of this combination also. Okay, so I'll not go into this detail. I think Prashant will be talking about this form when he explain methods of multiple scale. So I'm just sticking to this very simple form of harmonic solution. So yeah, coming back to this, so solution of this linear equation, we know that it exists like this. Now what about the term which is epsilon to the power 1? So here you see that so we took just two approximation. Okay, so we just took terms up to two approximation here. So term number 1 and 2. So now this x1 will also get like it will vary like this. So it is like d2 x1 plus x1 then minus 2d. Now you see here the first two terms are similar to whatever we had. X1 here it is x0 and here it is x1 dot plus x1. But interestingly, you will see that the right hand side term is a function of the solution of x naught, right? So after solving this, you got this solution, right? And this one you will have to substitute it over here. Okay, so when you substitute it over here, you see that you get an equation which can be solved and for a given like forcing which is written in terms of this x naught, right? So now coming back to this point, so here you will see that for the given initial condition which is mentioned here, x naught of x of 0 is 0, x dot of 0 is 1. So from this side we get a solution x naught t is equal to sine t. Okay. Now, for second equation, which was this, if you substitute it, it will become like this, and then your initial conditions will become like this. So when you solve this equation, you will get x1 is equal to minus t times x sine of t. So it means the total solution will be sine of t minus epsilon t times sine of t. Okay, and since we took epsilon for the bookkeeping, right, just to keeping, and just so we can substitute epsilon is equal to 1 and finally write the equation sine t minus t sine t, right? So this is the solution for up to first approximation. Okay, up to first approximation. This will not be valid for all the forcing. Okay, so it will be valid for only weakly for some epsilon. Now, what is the problem here? Can you see the problem? If the time period t increases, okay, if it is small, let us say from 0 to 1 second, if it varies, I can see that mostly the solution will be dominated by this, right? Now, and if you are multiplying it with the small number over here, so you can substitute that value. So it can be like if you remember your previous case, it was like 1/3, 3 factorial, right? 1 by 6. So eventually you will see that there will be a term which is smaller than the 1 itself. So it will very little less slowly as compared to this term. Okay, so this one dominates and this one doesn't dominate. But as the time t increases, right, let us say if not 1 to 10 or 1000, this term may be small along with this epsilon, but how long? It can be, because this is not, this amplitude of this term is 1, right? Amplitude of this term is varying as epsilon t. If epsilon is a small quantity, let's say if epsilon is 0.01, right? So if t becomes 100, then what will be happening? Epsilon t will become 1, right? Now when t increases 1000, what happens to epsilon t? It will become 10. It means that now this term is getting suppressed and this term is increasing. But is it a numerical artifact or it is happening in reality? The question is, we have just taken first two term approximation, right? So after time t greater than 1000, we realize that, you know, let us say there is a solution which was happening like this, and suddenly after time 1000, we realize that the solution is increasing because of epsilon t term. T is increasing, so the amplitude is increasing. Okay, so the solution is diverging, right? The solution is diverging after this time. So straightforward method is valid only for the small time. It is not valid for higher time because it will amplify the amplitude of one of the terms with with time, like after some cutoff. Okay, so that is the problem which is associated with your straightforward method. So then what is the solution? The solution is the multiple scale. Okay, so that's what I was trying to figure out. So this is a solution that you can get after solving the real one. You can get this from the maple. Okay, and here you see that the solution is valid for time which is of the order of 1 by epsilon. So you will have to decide if epsilon is 0.01. Okay, so it means the time t should be less than equals to 100. Okay, if epsilon is 0.1, you have it will be time t will be less than uh, uh, 10, right? So based on like what is the value of your epsilon, the solution of based on straightforward method will be valid, or it will represent a good approximation only for the time as long as it is less than equals to of the order of 1 by epsilon. Okay. Now to deal with this problem where the solution starts diverging after some time, the method of multiple scale is being discussed. In this case, so it may happen that there may be n number of times in a given system. Okay. So in the method of multiple scale in the given problem, we had, since we are having one term which is weak, and also there is one frequency component which is there. So we will assume two time in this case. Okay, one we will take original time t, which we will call as fast time scale. It is called fast time scale. Okay, and we will assume another time which we will be calling as fast sorry, this is a slow time scale. Okay, this is your slow time scale. It can even become, there may be, so one time let us call it as so this can be written as epsilon to the power 0 t. Okay, another time t1 can be written as epsilon to the power t. Third time can be written as epsilon squared per t. So there may be n number of times. So Tn can be written as epsilon to the power n t. Okay, so these are the different time scales that one can define to capture some of the factor that is that you want to and some of the factors that you want to capture using in different time scales, so you can define them accordingly, right? So this is your usual time scale, which is your fast time. As you keep on going over here, the time for if you try to process a system in this time, the process will become slow. If you want to process your system even slower, you can deal with this time. If you want to deal with your system even so much very slowly, you can go to even higher time. Okay, so that's what the significance is. You are just trying to stretch the total time basically for the system to complete, so it will play slowly, right? So that is the point that is there. Now using these time scales, we can apply perturbation method, and such kind of method is called method of multiple scales. Okay, so let us take again the same kind of problem here. So in this case, what we assume that your x is written as x to the x as a function of time t0 and time t1, and of course epsilon is there which will form the basis. So time t1 t0 is t and t1 is epsilon t. So you can write your solution, I'm sorry, you can write your solution, you can write your solution again in the same form, right, like we wrote for straightforward scheme. But here your each x0 and x1 will be a function of t0 and t1, t0 and t1, t0 and t1. This is important. Okay, now so you will have to find the derivative of each one of them. So let us say if you try to find out derivative of this in the real time, then since there are two times, so you will have to differentiate first of dou t by so this is your dou t by dou t naught, and then dt naught by dt, right? Similarly, if you go for t1, that will work like this. So whatever quantity is there, that will get multiplied like this, and the whole thing can also be represented as d naught. So d naught is the differentiation related with this time, right? This whole term that you are having. Then you are having this time, like with respect to your t1 that you are having. Now, from where this thing comes up? So there is some term which is skipped over here. So here you will see that, let me complete that term. So what was your T naught? T naught is T. So what would be T naught by dou T? It is 1, right? Similarly, what is your T1? Epsilon T. Okay. So dou T1 by dou T is really epsilon, right? So now if you expand this, so this can be written as 1 dou by dou T naught, right? Plus, what is the value of this? Epsilon, right? So I'm sorry. The value, so this is epsilon, so it is written as epsilon, and dou by dou T1, dou by dou T1 is written. So here essentially your D naught is nothing but dou by dou T naught, and D1 is nothing but dou by dou T1. Okay. So an epsilon is coming because of the differentiation of this time scale. Similarly, if you try to do a higher one, so this will become omega square, because there you will encounter d2t by dt. And what is t2? T2 is epsilon square t. So this will give you epsilon square. So that way it will go, and this will be called d2. Okay, so differential term will be written like d naught plus epsilon d1 plus epsilon square d2. So that way it works. Okay. Yeah. Similarly, you can do your second differential term, because you will require that as well. So this will work like this. So second differential term that you will be getting. So when you do this, you will get it like this: d naught square. So d naught square is d2 by d2 naught square. Okay. Then you have 2 epsilon here, single d by dt naught. Sorry, dou by dou t naught and dou by dou t1. And similarly, you will have these terms coming up over here. So after finding out these differential, this is your complete differential in terms of original time t, right? So there will be the differential term which will also be of the order of this epsilon. This is your original. Okay, but here you will see that in slow time scale, this term will come out. Okay, so you have to substitute all these over here, and here. Okay. And of course, x needs to be substituted from here. This x will go here. Now, if you do that, let's take an example and try to understand that. So let us take this example, which is similar to your Duffing oscillator, where cubic nonlinearity exists, right? If you remember, we were talking about theta double dot plus theta cube, right? So similar to that, you have cubic nonlinearity coming up. Of course, it is written the opposite side of equal. So accordingly, your alpha will also vary. So that way you can assume. But what is important is what is the order of nonlinear term. Okay, so here it is cubic and it is called Duffing oscillator. So in this case, initial conditions are gamma and 0. So to get the solution, again we will start with this, and epsilon naught, x naught, and all. And since t naught, t1 is epsilon, we will substitute all this over here, right here. So for that, we need to first find out first differential term, which is given by dou x naught by dou t naught, epsilon this and this, right? Similarly, second differential term we will get from here, and when you substitute it, what you are going to get is this first term, second term as a function of epsilon, then your this term, then epsilon 1, then epsilon, these are 1. Okay, so this way you are getting all these solutions, and yeah, there's a cubic term which is here, right? Now you see that when we write this equation like this, the terms, even the differential terms, are becoming of the order of epsilon. Okay, so after doing this, we will go and try to segregate the terms, and we will just take up to the first order of epsilon. So epsilon to the power 0 and epsilon 1. We are going to neglect higher order 2 or cube. All this we will neglect it, because when you have cube, you will have those terms coming up. So those higher orders and all you can always neglect, because this you can keep on expanding, right? This is x0, x1, x3. So this will also vary, and accordingly you will have, even with the first term, this corresponding to this term, you will be having epsilon cube, right? So we don't want to take those terms. We just want to take epsilon to the power 1 term and neglect higher order. Okay, so if you do that, the term which will remain is this. Okay, now you segregate the coefficient of epsilon naught and epsilon 1. So when you do this, you are going to get this equation, and then this is your second equation. So this is corresponding to this, and this is corresponding to this. Okay, so we have to solve this equation, and here remember that both of them are written as a function of t naught and t naught. Only t1 appears here. Okay, so the solution of this is very easy, which is your linear equation. So harmonic solution can be assumed as r of t1. So since this solution here, it is varying as t naught, so the t naught will appear here, but the terms which are there, they will be a function of this additional time t naught, t1. Okay, so r is a function of t1, phi is a function of t1, which is your slow time. Okay, this is, just remember, this is slow time. Now after you substitute this solution of this, so this is a solution of this, and you substitute it over here. Okay, substitute. So when you substitute, all these terms will become known, right? And when these terms become known, you can try to find out the solution over here. So when you substitute it, this is what is going to happen. Okay, now when you rewrite it, there is an interesting thing which is happening. Okay, so here you see, earlier we had a problem because we had a term sin t. Again we had a sin t term, and its coefficient was associated with this t. As the time t was increasing, this solution is also getting affected. That's why this solution was diverging after some time t. It means that we have to be careful with the terms which are related with that. It means the coefficients of all the harmonic term. Okay, if it is a time dependent, we should make sure that we should make it 0. Otherwise it will diverge, right? So when we, and those terms we define as secular terms. Okay, so it means this is the coefficients of harmonic terms, which may, and those harmonic term where the harmonic component is same as the solution of this, the first equation. Okay, so that way we try to define them as the secular term. Okay, so what are the secular terms over here? So here you see the other side, this sign. Okay, this is the sine term, right? This is the cos term, right? And what is the frequency of this cos? The frequency of this cos is 1, right? The frequency of this sine is also 1, and the frequency of this system is also 1, right? So since this frequency and this frequency and this frequency matches, we call them as the harmonic term of the same oscillator. But when you come to this term, the frequency is 3, right? Which is different from 1. So it will not affect this the solution which is near to this frequency. Okay, so we will not do anything, but we will do only the terms which are amplifying the amplitude of these harmonic, which is having the same frequency as the system's frequency. This is very important point in multiple scale method. Okay, and we make the coefficient of those terms equals to 0 to get rid of that secular term. So we will make this 0, which is r dash 0, and this 0, which is this 0. Okay, and from here you get the real equation of real evolution equation. We also call it as modulation equation, modulation or evolution equation. Okay, from here, because this equation is we are now proving only this r and phi of the solution, right? And here you should remember these all of them are written as a function of time t1. Okay, so phi dash is dou phi by dou t1, r dash is dou r by dou t1, but this time is t0. Okay, just remember. So it means that you have now got a equation or set of equation which varies with this slow time t1, and you have to solve for it, right? So now, so alternatively, so this is what you get it basically. R dash is dr by dt1, phi dash is d phi by dt1. Now you get this equation, right? This is what is called modulation equation. You substitute t1 is equal to epsilon t and this. So you substitute it. Now you come into the fast time, which is original time, which is t0. But it will add this epsilon term over here. You simply have to substitute at t0 this, and then epsilon will go to this side. This will become epsilon. That's how it is happening here. Okay, and this is 0, so it will not really matter. So after you solve for these two equations, solve for phi, solve for r. So after solving for these two equations, you can write your equation like this, right? So original equation was written like this, and these were the initial conditions. So here we see that your phi can be when you substitute your r naught, sorry, initial condition. So this is what basically you get it. So you can find your r naught and phi naught. It means the initial condition for them, you can, to solve this equation, you can find out from here. And after that you can so this is your equation. These are the IC's initial conditions, and by solving it you get r from here. It's a constant term which is given by this, and phi, if you just integrate it, so you will get this equation. So now you got r, you got phi, and when you substitute all of them into the solution, what was the solution that we had? And remember that the solution that we had was x is equal to epsilon to the power 0 x naught plus epsilon to the power 1 x1, right? So that way it went, if I remember it correctly. Yeah, so here x naught is the solution that you are x naught is the solution that you are writing. Just remember that. Okay, so the first term, which is so the first term that you get is given by this. Okay, so r is given by gamma, phi is given by, so phi, if you just substitute and you take your other term out. So for example, if you remember your solution back, so what was the solution that you wrote earlier? Yeah, so the solution over here, you see that you get I'm sorry, here it is. Yeah, r of t cos of r of t here and cos t naught and phi t. So we got solution of this and this. So we are going to substitute it over here. Okay, And so when we do this, this is what we are going to get. So just substitute these two things and we are going to get this. And T naught is what? T naught is time t, right? So that's what will remain here. Now the question is, what is this? So it means that you are getting a solution x which is written like this, and the rest of the terms will be of the order of epsilon. But if you try to compare it with gamma cos omega t, so you are having a new omega, right? And oh sorry, yeah, you are going to have a new omega which is given by this, right? So it means that your omega is 1 minus 3 epsilon alpha gamma square by 8. So your omega is going to change with the initial condition in this way. So when your omega is varying like this, it means it is becoming smaller. We call it as softening. When omega increases, then we call it as hardening. Okay, so because of this, and why it is happening, it is happening only because of the nonlinearity. Okay, so you can see that now, but another interesting thing is that now that the problem of divergence is gone, right? If you just see, the problem of divergence is gone because the amplitude of this solution is not a function of time. So there will not be divergence. The only thing will happen after some time, for a long time, it may happen that this will not be valid, but it will not diverge. Okay, so this will be valid only up to the first order of epsilon. If there is a large oscillation happening, you will have to take additional term and write this equation. Okay, so that's how basically we apply the method of multiple scale to get the solution of the simple Duffing oscillator, and this is the case that we described for free vibration problem because there is no forcing. Okay, so frequency is like this. Okay, so I'll move a little bit quick now because now we understand that how it works. So let us talk about averaging method. So in averaging method is different from multiple scale method. We don't deal with different times, right? But so what we do? So in that case, we assume the solution is on an average. Okay, so as the name suggests, on an average, we assume that the solution will be of this kind. Okay, now we will look for the value of R and phi in an average sense. Okay, so to start with, this is the first approximation that we do, and second approximation. So this is your first approximation, right? And the second approximation is and of course what this is the solution corresponding to when you deal epsilon equals to 0. So whatever solution you get, you will get it. Since it's a linear equation, you will get this one. Okay, now when you differentiate, yes please. Yeah. When you differentiate this solution, what you get is this. Okay, because R is a function of time, phi is a function of time. So the first term is minus R sine t plus phi. Second term, this is varying, so this will become R dash and this will remain same. And second, later on, you will differentiate this, so this will become sine t plus phi, and here you are getting phi dash and R. Okay, so this is your differential in usual time. But we are going to take an assumption. Okay, we are going to take an assumption that this term, this minus this terms becomes 0 in an average sense, and we will assume x dot is equal to only minus R sine t plus phi. Okay, only this term will be kept, and this term will be taken as 0. Okay, this is one very important assumption that we are taking in averaging method. After that, you make use of it, find out the x double dot because you require x double dot. So here you don't do that any further assumption. So that will become R dash sine t plus phi minus R, and then this way you will do it. and then you substitute these values in this equation. Okay, so this remains like this, and x double dot and x will become in this fashion. This is your x, this is your x double dot, right? Now the second thing that we are going to do is since this term is going to be assumed to be 0, so you will see that there are terms which are r dash, where is r dash cos t plus phi, and phi dash, where is r dash, one minute. So yeah, these two terms will turns out to be 0. Which one? Oh, I'm sorry. This and this will turn out to be 0, and yeah, so it is not because of this. I'm sorry. So it is just that they are equal. So if you do differentiation of this, and so and this is coming from here basically. So this and this will get cancelled. So what remains is this and this term. Okay, so this and this term will remain, and you are having this non-homogeneous term which is together. So we have to now solve this. Okay, so how we are going to do it? So what we are going to do it, from this equation you see that from the first equation in a sense, the assumption that we took equals to 0. It's a little difficult for me to go back and then come here. I think I should have stopped the animation. Yeah, let me, yeah, so here if you remember, this is the assumption that we took, right? So we will take this equation and third equation, so 2 and 3 we will use for finding out like the solution of our equation. Okay, so here, yeah, let me quickly, so this I already did it. So from first equation, we can just separate out this term, which is phi dot r, which is given by this. Okay, and substitute this one in the final equation that we obtained. So if you substitute that into final equation, this can be written like this. Okay, now from here we can simply have r dash. Okay, from here we can simply have r dash equation, and here you can just see that if sine goes here, this becomes sine square and plus cos square. So sine square plus cos square will become 1, and you will have simply r dash, right? And this sign will go to this side, and this will become, and minus can also go to that side. It will become minus epsilon sine and this equation. So ultimately what you are going to get is this from r dash, right? And similarly you can get from here phi dash. This will give you phi dash, right? I'm sorry. So this will give you phi dash. Here you can just substitute your r dash from here. Okay, so if you substitute r dash here, your phi dash is ready. So now these two equations are ready, and we need to find out the values of these equations, right? So the question is how to find out the values of these equations. So we are going to do approximation because this is a differential term. So how to do approximation? So if x dot is epsilon f with a time period of t, so one can do integration over that time period 0 to t, right, and epsilon by t, and that way we can write this average value of f as epsilon average, and this new x bar that comes up, which is your x average. Okay, so similar to, and it is valid for again this time period, which is t less than equals to of the order of 1 by epsilon. So using this function or averaging concept, we are going to approximate this like this. So your first solution, which is your r dash, is going to be approximated as this. Okay, in an average. So minus epsilon by t 0 to t, which is given by this, and phi dash is also like this. Now replacing t plus phi as some tau, so you can just substitute them over here. Okay, and and you can do integration from 0 to 2 pi now, because you have changed this t. So so this is the equation that you will get from here to here. Okay, this one from here to here in this time. All right. So after doing this, what we need to do is we have to approximate it. Okay, so when you do this integration, this will turn out to be 0. When you do this integration, this will give you some number, and when it gets multiplied, this is the solution that you are going to get. Okay, so it means that in averaging method, we are going to find out this. Okay, so in earlier case, this was like f of x, something like that. So this is for the duffing. We can take our f from here, right? Epsilon alpha x cube. So x cube term, if you just substitute it, so all these things will be quite clear. So if so, that way we get this average value of r dash and phi dash. So after getting average value of r dash and phi dash equals to 0 and this, we have to just solve it to get the solution. So what are the solution that you are going to get using these initial conditions? So you are going to get this and this as the solution, and ultimately you are going to have the same solution that you got from multiple scale. Remember, right? So this is the same solution that you got for the multiple scale. Okay, so let me describe one final method, and then we will close. This harmonic solution. Okay, harmonic solution is a little different. In previous one, you need to, so here you will see that only the one component of omega is captured, right? And you are not going for the higher component. So when your system is having multiple frequencies, so it is always desired to go for harmonic balance solution. Okay, this is not harmonic, but it's called harmonic balance. Harmonic balance method. Okay. So in this case, again, let us consider this equation. So approximation over here is we express x as a summation of all harmonics. Okay, earlier we just had only omega, but here we are going to express it as a function of all harmonic. So we can write it as ai cos j omega and j omega naught. All right, and we will substitute it over here by differentiating it. So if you differentiate it, so what we do after differentiating, we will get these many equations. If you, so first you have to substitute it over here, okay, and then compare the coefficient of all the harmonics. Okay, so when you compare the coefficient of all the harmonics to 0, so or compare the coefficient of harmonic both side. Okay, so that is precisely correct. So in that way you are going to get n plus 1 solution, equations. Okay, you have to solve for those equations to get the solution. So so what we do in the first solution, if the harmonics of first solution, that will be given from the coefficient of your cos omega t plus phi naught t, and that can be solved from the initial condition itself. And rest of the equations can be expressed in terms of these known, which will be obtained from the initial conditions. Okay, so that is more or less the step that we have to follow. And the important thing is that this method is useful when some knowledge about periodic solution is there through the experiments or numerical result. Otherwise, one will have to take many terms to get things. Okay, so very quickly, let us take another kind. So here I'm taking this Duffing equation. This is in the opposite side of equal with the plus sign. So I can write this, since there is a cubic order. Okay, just remember, since there is a cubic nonlinearity, so I will not be taking A2 term. Okay, A2 term I am not taking here, 2 phi naught. So this term I am not taking, only the cubic, because the cubic term may amplify and that harmonic may amplify. That's why that term needs to be taken. So we are taking omega and 3 omega term, which is hello. Yeah. So after this solution, we can differentiate it once and then twice and substitute it into this equation. And assuming this psi is equal to your omega t plus phi naught, and then we can compare the coefficient of cos psi and cos 3 psi. So you will getting two equations, 1 and 2. Okay. Now you will see these terms are higher order terms. Okay, so we will just take first terms of these in both the equations and solve for it. How it is? Here, if A3 is of the order of A1 cube, right? This is what it is visible. If you see this equation, what is the first term? A1 cube. So if A3 equation is of the order of A1 cube, right? So it means that these terms will be of the order of A1 5. This term will be of the order of 9. It means they can be neglected. Okay, so we can rewrite this equation as this equation as this. Okay, and then we can solve for it. From here you will get omega. Okay, omega will be given by this equation, and omega is square. Basically, if you take a square root and approximate it, this is what you are going to get. It is same as what you obtained previously, but with a minus sign because we took nonlinear term in the other side. Okay, so this and A3 term, you will see this is what you are getting, right? It means that up to 2 harmonic you are getting this solution. So from multiple scale and averaging method, we were getting only this solution, but this was missing. Higher harmonic component were missing, right? But using harmonic balance, you can always have it. Okay, so that's how basically we try to apply these methods, and there are many applications there where you can see it, like shape memory alloys, where you see that its characteristic varies non-linearly, right? Something like this. So if you club it, let us say you have a beam, you have a shape memory alloys inserted in it, right? So because of the temperature, it may bend, and if it is also vibrating for a large oscillation, you will see that the nonlinearity may also come up. And by operating it into the higher oscillation, you can always tune these nonlinearity from softening to hardening. These are all the nonlinear terms. Here you can see beta naught cubic nonlinearity, beta 1 quadratic nonlinearity. You can solve these equations using harmonic balance, and you can just try to have all this. Similar to that, not just SMA, you have your vehicle modeling when you do using half car model. There also you come across your non-linear for jerk that you get it right. So you try to control it using suspension system, and you see that these are the magnetic suspension system. Here you can see how it works, right? So the characteristics of a damper basically is something like this. Again, to club this one with this dynamic equation, you need this expression, and when you try to see how it looks like, the first approximation is that this stiffness term is having cubic nonlinearity, and damping term may also have some nonlinearity from these characteristics. Okay, so these are very important, at the characterization state itself, you will have to see whether you are taking the non-linear characteristics or linear characteristic. And then when you write the equation of motion for this, let us say this is your Z1, is the front one, sorry, this is rear, this is the front of a car. So let us say here is your car, right? This is your front, and car is moving this way. So front one is this, rear is this. Now if the CG, let us say if there are many passengers sitting over here, and if the CG moves, right? If the CG moves, what will happen? This will shift, and correspondingly your Z1 and Z2 will move, right? So because of that, and also since we are using suspension system, and those characteristic is decided by this forcing, which is having non-linear terms, right? So that can affect both the motion. Okay, so this is the motion for Z1, which is associated with your rear, and this is the motion of your front, which is associated with this, right? So an excitation is this, is the road excitation basically, And here you see that there is another important thing. The excitation which is received at the front will be received by rear after some time. So there is a phase delay, right? It means there is a delay which is coming here. Delay is also important in such kind of system, which Prakash will talk about tomorrow. Okay, so you are having two systems which are these, and you can just see here. You can try to find out the solution of this using multiple scale. You can do simulation using numerical methods, and then you can. This is the response of Z1. This is the response when both try to interact with each other. This is called nonlinear interaction which is happening. So response of A2 is getting affected because of the response of A1, right? When you try to sweep the frequency in the first one. Okay, so these are the interesting thing that comes up, and there are a lot of application. Even in the MAMS it is there. I will not go into deep, which Prashant will talk about in the second half, but I will just show you. I will end till this reason that what really happens in MAMS, so that you will follow that exercise better. So what is happening when you apply here you are applying voltage, right? Here you are applying voltage, here you are applying voltage between the top and the bottom one. So when you apply voltage, electric voltage, this moves up and down. You know, this can be captured using laser vibrometer. So this is your parallel plate capacitor, this is your torsional kind of mirror, and this is your cantilever. The same thing, like electric force will come up. But these devices are so thin, if you increase the voltage, they may cross into the nonlinear resin. Okay, so those nonlinearity basically can be captured. So this is the equation. So this is your linear mass, linear spring, and this is your electrostatic force. Here you see that displacement is appearing, and if you explain this, if you expand this term using Taylor series, so you will see that there is a nonlinear term which is coming up, and here the nonlinear term which is coming just for the expansion of this. Okay, so here this is a function of u, and here is also u. It means that this term force is developing some stiffness equivalent term, and when you take it to the other side, this will become k minus electrostatic. It means that if your displacement is increasing, this stiffness reduces, and it will be affected by this forcing. But on the top of it, we also have u square, u cube. So it means that you have cubic nonlinearity and quadratic nonlinearity coming from the electrostatic forcing. Okay, so your system can have this nonlinearity, and one has to really understand how it all behaves. Okay, so again, as I said, because the k is changing, so your frequency is a function of this voltage, and you will see that omega frequency will also reduce because of this term as voltage increases. Okay, and then you can find out the solution as we were trying to find out. This is your own nu omega, which is a function of cubic term, quadratic term, right? And this is your solution u. And when you deal with forced frequency, which Prashant will be talking about, so this is the kind of response that we get it. Okay, this is where I'm going to stop now. So here you see just a MAMP system has introduced different kind of nonlinearity, and when you compare those system with this Duffing oscillator, based on the sign of this cubic nonlinearity, if it is less than 0, you see a response which is softening. If it is more than 0, you see a response which is hardening. And what is happening here? This is a very unique solution. So what is happening in this case? So in this case, it is increasing, and from here there is a jump, and then you will come like this. Now when you reverse sweep, it will go like this, and then it will jump here. Okay, so but this is your solution, which is unstable solution, which you will get from only multiple scale or bifurcation tool using MATCON. You will not be able to get it either experimentally or using Rangakuta method. Okay, so these are the jumps that we want to capture in nonlinear system, which is very crucial. And important thing is you don't have now this frequency being constant. It varies with amplitude, right? So the concept of natural frequency ends here. So this is a resonance frequency which is varying with your amplitude. Earlier for linear system it was constant, right? Okay, so I would like to end my talk here, and Prashant will take up further, maybe around, since we have taken the time, more time, so he can start little late if you want. But as of now, we will just keep it as like 2:45. Okay, so if you are having any question, please do ask me. Thank you.